Okay, we're on to the second half of this first unit. Listen up, folks, let's roll. So this first unit is technically on thermochemistry and rates of reaction, but I like to separate it out just because it would be way too much to drag this on and have a super huge test at the end of the whole unit. In terms of the timing is a little off in that the first half takes a lot longer, and this chunk, I actually, if I went straight through, if we didn't have the fog day, I could have been ready for a test next Thursday because there's not a lot of stuff. There's not a lot of stuff in this second half, but it is important. But I'd rather separate it into a smaller second test. But with the fog day, that pushes me back to the Tuesday, right after the long weekend. So what I had done was I had removed a lab to make it fit. Then the fog day came in. So I'm going to put the lab back in. So then that pushes a review day after the long weekend, and then the test on the Wednesday after the long weekend. So I'm putting the lab back in to just kind of push everything back so that it doesn't become test on the Tuesday after the long weekend, which I don't think would be beneficial to you. All right. So it's a shorter half. It's not really broken into halves, but it's a shorter chunk. So we're aiming towards a test fairly quickly at that point. Okay. Chemical kinetics, it's chapter 6 in the textbook. Again, just like when we started talking about thermodynamics, we needed a day to kind of just talk about what we mean by chemical kinetics, how do we measure various things, what we're going to do with these measurements, and then in the end, how does this impact our analysis of a chemical reaction? So chemical kinetics is the study of rates of a chemical reaction. This is something we don't talk about very much, not in great detail. You talk about it a little bit in grade 9 and 10. I don't even mention it much, just maybe a little bit in grade 11, but it has to do with speeds of reactions, all right? Some reactions are very quick. If I have hydrogen gas in a balloon and I supply it with a little bit of energy, that combustion reaction takes place very quickly. But then something like oxidation of iron, rusting essentially, is a slow reaction, and it can take place over many years, very slowly oxidizing the iron. Both of them are oxidation reactions, whether I'm burning the hydrogen or oxidizing the iron, but for some reason one is very fast and one is slower. And you've talked about that in the past. Factors that affect the rates of reaction. Does anybody remember some of those factors? It would have been a list. Things that cause reactions to go faster than other reactions. And if you don't remember, it's not a big deal. Anybody? Anything? No? Something like, what's that? Presence of a catalyst, right? If there's a catalyst there. Things like concentration. If you have a highly concentrated something and you put something in it, it reacts very quickly. And things like temperature. If it's warmer, it seems to react faster. You would have made a list of those things and then maybe just kind of regurgitated them out on a page for a test. We will be looking at exactly why those factors affect them, all right? So we will be looking at, on a molecular scale, why do we have, faster reactions if we're dealing with a catalyst? What does a catalyst actually do, all right? Okay, and again, that discussion deals with energy, okay? There's a link between this discussion on chemical kinetics and energy because we have to talk about how much energy it takes for that reaction to kind of get going and get initiated. All right, so let's talk next about defining some ways in which we measure reaction rates. Let's bring the whole thing up. Let you write and then I'll talk. Oh yeah, you bet. I don't know. She used to teach chemistry, so I think she's just checking out, see what we're doing. I lost my train of thought moments ago, but I got it back. In the end, at the end of this little unit, and the purpose of studying a rate to such great detail is that chemists have the ability, and I'm going to show you how to do this, to actually get an understanding of what's actually taking place in a chemical reaction on a molecule by molecule basis in terms of how they collide and how they behave and what's actually taking place in a reaction. And we can get that information from the rates, from how quickly they react. Yep. Yes, change in time. I'm going to talk about this in a moment. I just wanted to say one more thing before we get into this introduction, into this mathematical part. I said it a moment ago, but many of you were still writing. One who studies chemical kinetics, and kinetics, chemical kinetics is very similar to physics kinetics, where you've got a speed, right? You've got like a velocity for the reaction, but it's not really a velocity. It's how quickly things are reacting. The purpose of a chemist that studies chemical kinetics is to get an understanding of what's happening right during that chemical reaction. What atoms are interacting with other atoms as a reaction happens. In grade 9, 10, and 11, we give you this kind of poof view of a chemical reaction. I even used it when I introduced the thermal chemistry, where I had, with my awesome graphics, chemical reaction with the cloud around it, right? The good graphics, remember that stuff? No, you have no idea what I'm talking about. Anyway, so we, as chemists, when we introduce chemistry, we say reactants, arrow, products, that's all you need to know, balance it up, way to go, you're a chemist, good job. But that arrow represents a process. If it didn't, it would literally be magic. We would have, poof, products. That's cool. But in reality, there is intermediate things that are happening. Bonds are being broken. Atoms are being rearranged. Kind of half bonds are broken and half bonds are being formed. But in the end, we end up with products. And the goal of someone who studies chemical kinetics is to figure out what's happening during the arrow. The arrow becomes the most important thing for someone who studies this. If you can figure out exactly what happens during a reaction, perhaps you work for a pharmaceutical company, you've got your chemistry degree, you got a master's, you do great organic chemistry. If you can figure out what's happening during that arrow for the reaction that produces a very important, pharmaceutical chemical, and you can then manipulate the way in which that happens, maybe by bringing a catalyst in or adding another chemical that lets that reaction happen easier, then you will save that company piles of money. If you can do it such that the amount of energy required to make that molecule decreases, you're going to save them a lot of money. If you can increase the rate in which it's being formed, and in other words, they can make it quicker, more efficiently, you're going to save them piles of money. So that arrow, what's actually happening in a chemical reaction as the reactants are breaking apart and the products are being formed, is a very important thing to know. We can get all of that information by starting with how quickly does the reaction happen, because the speed at which that reaction happens is a little indication on what's going on in the arrow, all right? And that's where we start. So right here, I'm starting it with the basics. the first thing that we need to be able to do in order to study a reaction. Determine the rate, right? We're going to call that R. And it's not a speed, it's not like a delta D, but we're talking about how the concentration of the reactants changes over time. I've introduced you to the square bracket notation. I would have used it when talking about concentration of acids, right? The molar concentration of H3O+. So when you see the square brackets, and we're going to be seeing them a lot over the next 2 units, you need to be thinking moles per liter, all right? So that's a molar concentration. So the rate of a reaction, the rate in which a reactant is consumed, the change in concentration of the reactant as it goes down with respect to time, all right? But we can also think of it as the rate in which a product is produced. You don't have to look at the reactants disappearing. You could also look at the products being produced. The rate in which a product is produced is the change in concentration of the product as it grows with respect to time. You might think that these should be opposite. As a reactant disappears, a product forms. And that's a true statement. If this were in a physics class, we would get really picky about the signs, right? The negative rate of reactant would be equal to the positive rate of product. Chemists aren't worried about disappearing or appearing, all right? So we don't talk about signs. We just talk about the rate of the reactant disappearing, all right? And we don't put a negative in front of it. So the signs we would just leave as the same. We would just represent it with words. The reactant disappeared at a rate of this, the product appeared at a rate of this, okay? And this is a delta, which means a change. So it's the concentration of the reactant final minus the concentration of reactants initial, just like in physics. And this is a delta T, it's a change in time, all right? So this is now time and not Celsius temperature, like I said, little t the other day. So that's a change in time, all right? We'll do some example problems in a moment. Okay, actually, the moment is right now. I forgot it was right there. Okay. Again, just a little check, and I haven't asked in a long time because I forget every time. How many people here have not taken the grade 11 physics? Not taken the grade 11 physics. Ouch. That's fun. Okay. Then I get to do this at an annoyingly slow pace for those of you who have taken the grade 12 physics, because this is exactly the same as finding the speed, right? Which is the first equation you use and learn in grade 12 physics. Or grade 11 physics, I mean. Grade 11 physics. So a chemical reaction has taken place. It decomposes to produce NO2 and O2. The concentration of NO2 changes from 0.2 molar at the 1 minute mark to 0.65 molar at the 4 minute mark. NO2 is a product, so it's growing in concentration as the reaction proceeds. Some observations were taken, how they determined that concentration. We won't worry about that right now, but they just did. We'll talk about how we can measure some of these rates later on. I want to determine the rate, R, and because I'm dealing with NO2, that's the product that I'm dealing with. So if I'm going to write this out very rigorously, it's the concentration of NO2 final, and I'll put an F instead of 2. Sometimes I can use 2 and 1, final and initial, but I'll use final and initial because I've got 2's all over the place, all right? Minus the concentration of NO2 initial. Yep. It doesn't matter in this case. There is no standard rate unit. We can leave it in minutes. In this case, I'm going to leave it in minutes. If I give you data in seconds, you can leave it in seconds. Over T final minus T initial, and that's going to get us our rate. The final, 0.65 molar, minus the initial, 0.20 molar, over the final time, 4.0 minutes, minus 1.0 minutes. That's going to get me what? 0.45 molar over, what is that, 3? 3.0 minutes. And I'll take that number when we get it. Yeah, Jess? 0.15, 2 significant digits, very nice. And that becomes moles per liter per minute. Because remember, molarity is moles per liter. Moles per liter per minute. Okay, yep. You could put capital M per minute, that would be fine. I just wanted to stretch it out to remind everybody what it means. Okay, all right? And that's a rate of production of NO2, okay? No need to rewrite the chemical reaction. I just have it there for reference. Just write B, and we'll do the second part of this question. Once we know the rate of consumption or formation of one of the reactants or the products, we can then determine the rate of consumption or formation for any other reactant or product straight through stoichiometry, all right? So in this case, the rate, oops, and because I, for some reason, want to change that. In this case, then, the rate of consumption of N2O5, that's just a subscript, because I want to just separate it out as the other rate that we did, is going to be equal to the rate of formation of NO2 times a conversion factor that's going to relate the amount of NO2 to the amount of N2O5. We have a term for this conversion factor that relates to reactants and products in a chemical reaction. What do we call that conversion factor? Where we relate reactants and products amounts? Yep, mole ratio. That's all you use is the mole ratio. The mole ratio simply relates the two. So I want to get rid of this 4 to 2, and that will get me the overall rate. So I can take my previous rate, 0.15 molarity per minute times 4 to 2, turn it into what I want, and I can then easily figure out what that rate is. You got a number? 0.075 molarity per minute. Okay? All right? Instead of it just being a number of moles, it's a molarity per minute, but it's related through the same thing. For every, for every 4 moles of NO2 that's produced, 2 moles of N2O5 will disappear. So we just need to use the mole ratio. So for those of you who are thinking back to last year, that's just the mole ratio. That's all that is. What I have on the bottom, what I want it to be on the top. Okay? Don't write that part on the bottom. That was just the part where I was just saying that we don't worry about the sign. Technically, it's negative. right? It's because it's a disappearance, but we don't deal with the sign. We're just talking about how much of it is being consumed instead of produced. All right, we just say that. Okay. And one last one, rate of production of O2, just to practice it up there. You guys can go ahead and do that one. I don't need to necessarily see the nice equation for it. So the rate of production of O2, and you can just go back to a previous number. Really doesn't matter which number you use as long as you use the mole ratio that goes with it. I would start with the 0.15. That's what I would do. I'd go back with that guy there. I can write the equation out. That would be the rate of NO2. What's the conversion factor going to be in this case? Yeah, Christian? 1/4. Yep. So 0.15 molarity per minute times 1/4, and what do we got? Yep. 0.0375 molarity per minute. We'll keep the 3 significant digits. We're dealing with not whole numbers, but fairly nice numbers. We should round it, but I'll just leave it right like that for now. Okay? All right? So that's how we actually calculate them. Now we just got to go over some definitions. Average versus instantaneous. Yeah, just like we're doing grade 11 physics. Average velocity versus instantaneous velocity. Average rates of reaction versus instantaneous rates of reaction. Reaction rates are never linear. There is no constant speed for a chemical reaction. A chemical reaction always initially begins at its fastest possible rate and ultimately slows down and stops. The reason the initial rate is so fast is because all of the reactants are at their maximum concentration. They're all there. As the reaction proceeds and the reactants become products, the amount of reactant molecule is less. They bump into each other less frequently, and there are less successful collisions that result in products, and therefore it slows down. And therefore, it starts at its steepest possible rate, the steepest slope, and it then declines to a lowest possible rate of 0, a slope of 0. This graph represents reactants. Don't worry about putting the lines. If you're sketching it, just sketch these graphs, all right? When you do the homework problems, there are some that ask you to draw a graph and do some measurements. And I do have an assignment a little later on in the unit that I'm going to make you draw a graph and analyze it. And tomorrow we have an experiment where we're going to get our own data and you will draw a graph and analyze it. But for now, just draw a sketch, right? Concentration of reactants. You could even, when we're sketching these things for today's note, just put things like this, right? Or even just concentration. Because I could put a graph that represents what happens to the products. What would the product line look like? What would the product line look like? Sarah, what do you think? Flipped around, start at 0, nice and steep because it's being produced really quickly, and eventually the reaction stops, right? So you're right. If I were to do a product formation line, it would look something like this. Now, it wouldn't necessarily have to line up with that. It would if its stoichiometric coefficients were 1 to 1, right? But if it was like, say, 1 to 1/2, then it would end up going only to half the height and moving along there. All right? So that would be a product line. All right? And in this case, if this was A and the product was B, it would be something like 2A produces B, right? In other words, there's only half the B being formed, right? So it doesn't have to go to the same spot. And it could have went higher. If it was like A equals 2B, it would have went to twice as high, okay? But product lines are growth lines, all right? They're growing like that, okay? All right, so that is essentially a concentration versus time graph. Now let's talk about what instantaneous versus average rate is. Hold on 1 second. Don't worry about that. This can be shown graph. Just put the bullet underneath. As the reaction proceeds, products increases. Don't redraw that. I just put it on the last graph. Just write the bullet. I should actually get rid of that slide and just draw it on every time. So just write the first bullet. As the reaction proceeds, the concentration of the product increases, and you drew that on your last sketch. Okay? Again, steepest at the beginning. Most products are being formed at the beginning. The products are being formed at a great rate at the beginning. And then at the end, the amount of products being formed slows down because it's almost all products by the time it's at the end. Okay. Average rate. The change in reactant concentration or product concentration over a given time interval. So this is over an extended time interval. Now my next slide has a little diagram that indicates what a secant is. I'm going to just go right over that, and I'm going to go to the definition of what an instantaneous rate is, have you write that down, and then we can compare the difference between an average rate and an instantaneous rate so that we can get a good understanding of that. If you had all taken physics, I wouldn't have to go to this much detail. But that's okay. We won't discriminate. Instantaneous rate. Again, don't bother drawing the sketch. I'll go back and we'll draw a sketch to compare the two. Okay, let me talk a little bit about average rate versus instantaneous rate, just quickly again for the non-physics trained. A good example to describe this would be talking about the speed of something like a car. Let's say that you're driving down the road and you're in behind a slow mover, all right? I like to call it granny, perhaps, right, if it's a slow mover. But it doesn't necessarily have to be an elderly female. It just, we'll go with granny as the term. And you're driving slowly and you finally get the chance to pass, so you take it. So you step on it and you accelerate, and you might have to break the speed limit as you're passing, especially if they're right close to that speed limit. So you got to break the speed limit for a bit, and then you've got to slow back down and get back to going a regular speed. And your graph for that particular thing, if it were rate, right, or a speed versus time graph, might look like this. Here you're going the slow speed, and then you got to speed up to the higher speed, and then you got to slow yourself back down to the slower speed. All right? Okay? Now, the average rate, or the average rate of that particular thing would be somewhere in the middle, what your average speed is. And the way you would get that average speed, it's not an average speed, it's an average acceleration. I got to watch what I'm saying. But, no, that's a distance time graph. Don't I need a concentration? Yeah, this is a distance time graph. Haven't done my physics in a while. It changed it. You're driving along, going a certain speed. Then you speed up to a higher speed, and then you slow back down and keep doing your regular speed. All right, that's what that graph's going to look like. It doesn't matter what the appearance is. The key thing is that we got a curve on it. To get your average speed, what you would do is you would take your line, find the 2 points of interval that you're interested in, right? Take that T2 and that T1 and subtract, and take that position 2 and position 1 and subtract, and you'd end up with a line that cuts across there, all right? And that would be your average speed, all right? But unfortunately, if a police officer were observing you at the point in time that you had to speed up and take off and do a higher speed, they might actually measure you over here at this point in time. We'll pick this one right here. And they might say, you're speeding, I have to give you a ticket. And what they've measured is what your speed is right at that point in time as they're driving by you. That would be determined by the slope of a tangent, a line that just grazes the curve, all right? So the slope of that guy would be your instantaneous speed, all right? This is going to be your average speed. You can see here that your average is not as steep as your instantaneous speed. It means that maybe for a brief moment, that brief moment in time you were speeding, but overall you've generally been good. You weren't speeding on average. Come on, I was just passing somebody. Give me a break, right? Same thing for a chemical reaction. Let's go back to this particular graph here, just because it's larger. In a chemical reaction, and do a quick little sketch again, and don't write necessarily concentration of reactants. Let's just go with square brackets R, just to speed things up. Square brackets R. Same with this, elapsed time. Just write time, even put T down there. The important thing is the shape of the curve. And then just put our curve that dies away that we saw initially. Okay? And then just draw a line on there that touches 2 points. And that's what a secant is. A line that just connects 2 points. All right? And if I wanted to find the slope of that, I'm going to have a T2 and a T1. And if I work my way across here, right there and right there, I'm going to have a concentration of R at time 2 and a concentration of R at time 1. And that average rate, all right, is going to be equal to the change in the concentration of R over the change in concentration of time. Subtract those and subtract those. And that's the equation we just learned. The equation we just learned is actually an average rate equation. Graphically, on a graph, join the two dots that you're interested in, the 2 points in time, find out how big this is right there, delta T, that's what that is, that length. Find out how big this is, delta concentration of R, put it in the equation, and you have the slope of the tangent. Sorry, the slope of the secant, thank you. The slope of the secant, the slope of the line that joins the 2 dots. I never used the term secant when I taught physics. I just said, connect the 2 dots that you're interested in, find the slope of it, right? Okay? I'm a classic believer of good old slope equals rise over run. Don't get bogged down with x2 minus x1 over y2 minus 1, all those funny equations that math people have you memorize. The rise, delta R, the run, delta T. Okay? All right? That's average. If we wanted the instantaneous, let's say I wanted the instantaneous rate at some point down here. I'm just going to pick a point. And you can do that as well. Pick up, oh, look at that tiny little graph. There you go. That'll be exciting. Oh, more tiny little baby graphs. That's fun. To find the slope of the tangent, you would take a ruler, all right? You would adjust that ruler such that it only touches the graph at 1 point. Ta-da, right along there is my shadow. Now, unfortunately, I can't actually use a ruler to draw this because I can only touch 1 point at a time. But that tangent, I'm going to make an estimate, is just kind of running along here, touching at 1 point. Hey, that's not bad of a tangent. I've had worse. The neat thing about finding the slope of a tangent is you can extend it as long as you need to until it finds 2 good spots on the graph. If I were extending this one, maybe I'd extend it out to here and I'd hopefully get to that little spot right there. That's a good one. If I extended this out to here, oh, maybe I'd get to that spot right there. However long I need it to be, as long as it touches that line, and then I could get there the rise, and along here I could get the run, and I could put it in my slope equation. I could get the slope of that tangent. Okay? And therefore, this guy right here is the instantaneous rate. And this guy right here, the slope of that secant is the average rate. Okay? And that's the difference between the two. One is, what's the rate now, at this point in time? And the other one is, what's the rate across from this time to this time? That's essentially the difference between them. Okay? I'm going to go back one more slide here. When you get a data table, you can either make a graph and find the line, and I'm going to actually get you to do that, and the best way is to do it graphically. The most thorough way to analyze your data to get an average rate is to do it graphically, because there's always errors that can make it fluctuate. If you've got random errors in your experiment, your line isn't going to be beautifully smooth. It's going to have some little, jumps to it. So the curve is the best way to do it. But if you were in a pinch and you were in a hurry, you could actually just take 2 data points and just do your good old rate average is equal to delta R concentration, delta T, and that will also get it for you. That's our equation we learned just moments ago. They're actually average rate equations. So if you were in a pinch, you could take 2 points, take the T's, subtract, take the rates, take the concentration of reactants, and go. All right? Oh, and I should be careful here. That means rate and that means reactant. Ooh, I think we're okay, but I got to be careful with that. Got to be careful. Okay, let's do an example. Now, don't write this down. Don't write it down. I'm going to give you practice problems to do. But what I used to do, I used to say, okay, let's write it all down. Here's a piece of graph paper. You'd take 10 minutes, you'd make a nice graph, and then we'd analyze it, and class would be over. I think you guys know how to make a graph, right? I just want you to see me do some of the calculations, so when I give you the homework, you're making a graph and doing the homework, okay? If you get information like this, and we ask you to plot it on a graph, I think you can handle putting concentration up to one side and time along the other side. And when you do that, it's going to look like this, all right? I had that graph made. So you do that, you put the concentration versus time, and now we want to answer some questions. Determine the average rate during the first 600 seconds. I want to do this 2 different ways to see if we get the same answer or not, to see if there's random errors in our data here. If I were to do this straight off the table, I would get my rate, right? If I was just figuring it straight off the table, is equal to, well, if I'm looking at the first 600 seconds, right? My concentration 2, 0.69, my concentration 1, minus 1, over my T2, 600, minus 0. If someone could do that calculation for me, that would be great. Yep. Negative 5.17 times 10 to the negative 4, and that is going to be molarity per second. Okay? All right? And you'll notice we have it in seconds in the bottom, so it's going to be a small number because I've got a big number in the bottom. There's nothing wrong with that. That's a good number. Now, that's just simply by taking the data points. That's the first way you can do it. Let's do it graphically. So, graphically, we would make a graph like this. We would find 600 seconds. There it is right there. 600 seconds. 0 right there. Join the 2. Right? Read the time. It looks like the time is right there and right there. All right? And now let's get the data off of it. And I'll write it down here maybe in black. So, the slope is equal to rise over run. What's the rise? What is this number? 0.6 and 0.7 is right in the middle, isn't it? Right? Notice how it goes up by 5. 1, 2, 3, 4, 5. And that's for 2 of them, 2 units. So 0.7's in the middle. I got to do a quick calculation to figure out what each square is worth. So each square, this is 0.2 divided by 5. Each square is 0.04. That's up by 2. So that's times 2. So that reading right there is 0.608. You wouldn't write this on there, but that's what that value is, and that's 1. So my rise is going to be 1 minus 0.608. All right. Technically, it's actually moving down, but that's okay. And then my run across is 600 to 0, so that is going to be 600 minus 0. 600 minus 0. So could somebody do that calculation for me? Yep. Yeah, I did. I did it backwards on the top. Flip it over if you want to flip that over. I did one backwards, but we'll get the same number as long as we ignore the negative sign. Is it? Yes, it is. 6.8. Thank you. Thank you very much. Had a decimal issue. What do we have for a number there? Yeah, just what you got? 5.3 times 10 to the negative 4, and that again is molarity per liter, okay? All right. So we might get something a little different because we had to estimate what's going on in here, but this might be a better measurement than the last one because there could have been fluctuations in our data, all right? One is straight up from the data points, the other one is from the graph, okay? Just a rise over run. I'm going to go back and take a look at the next one. Let's just go with the instantaneous rate at 600 seconds because I'm just looking at the time. The next one is another average rate between 1,000 and 1,600 seconds. Again, if I were doing it with an equation, the average rate, I would pick this and this and this and this, right? I put it in my equations, get the number. If it was the average rate on the graph, then I would be looking at, and let me just do a little clear here, clear ink. If it was an average rate on the graph, I would be connecting 1,000 to 1,600. I'd draw a line. Again, I'd find rise over run, okay, for average, all right? And I'm going to clear this, and we'll quickly do an instantaneous one. Clear ink. Let me go back. The clear ink here as well. So instantaneous at 600. Cannot get instantaneous from data table because I need to know what the tangent is. So at 600, this becomes difficult on the smart board, but what I need to do is I need to take, what do I do with that little ruler? I'll take this big ruler. I need to take a ruler, and at 600, I need to draw a tangent where it just touches it. I have to freehand this, so I'm going to try to come across there, try to come across like that. Yeah, it's got a curve to it. You'd use, obviously, a nice ruler. Again, the nice thing about drawing a tangent, you can extend that as long as you need to until you get some nice spots. So I would say that's a nice spot because it hits a crosshair right there. All right? Because that means I'm going to be able to look straight down on this number and straight over here on that number. Okay? And I'll just keep going until I get another nice spot. And because it's curved, it really doesn't have a lot of meaning. But there's one. That's not bad. And so therefore, if I can figure out what that rise is there on my graph paper and that run is there, then I can get that instantaneous. All right? Again, each one of those is what? 0.04. So if I go up by 1, 2, 3, 4, 5, 6, 7, 7 times 0.04, 0.04 times 7, 0.28, and this goes up to, this is 1, 2, 3, 4, 5, 6. That's 600 seconds. It just turned out. All right, that way. And therefore, my slope of the tangent is going to be rise. It's actually negative 0.28, but we don't concern ourselves with negative for chemistry over 600. And if someone could just do that calculation for me briefly, then we would have a value. Elaine is looking at her calculator. She's counting significant digits. What do you got? Times 10 to the negative 4? Negative fourth molarity per second. Okay? All right? Okay. Practice problems. Some graphs are given. Sometimes they give you a data table, and if they don't say make a graph, you, for average, don't make a graph. Just do the calculation. Pick the two numbers. Okay? There is one more little piece to this little lesson that I'm not going to get to. I'm going to let you look at the questions, and if you have any questions on how to do things very quickly, I can answer them. But there is one more little piece to this lesson, and I can do this at the end of, after the lab tomorrow, because the lab doesn't take really the full class, is how do we measure these things? How do we actually measure a concentration of reactant or product in the laboratory? So the next bit is how do we actually measure the rates? One of them is production of a gas, and that's what we're going to do tomorrow. Tomorrow we're going to react some magnesium metal with hydrochloric acid. We've done that reaction many times before, but it's going to produce hydrogen gas. And we're going to collect that hydrogen gas, and every so many seconds we're going to write down how much is produced. Then we're going to get a nice graph of production of hydrogen gas. So what we want to finish off with this first introductory note is physical properties that we can measure, that we can actually convert into reaction rates. All right? Stop this thing for a second.